We were in the middle of discussing or finishing off the Markov thing, and this example here, so I've seen a couple of bad things about Markov, some really good things about Markov, but mostly the approximations are pretty coarse. We're going to go back to the intelligence example and refine Markov in two different ways. Okay, so that's going to be the goal of today, and hopefully we get to do the voter poll example at the end. Okay, before I do that, I just want to, I spared some writing so that I could get through the example last time. And I just got through it orally. I should do some writing, so I'll just briefly do a little bit of writing. Okay, so in the hats example where everyone's redistributed their hats, if we have an indicator variable h1, or sorry, hi, h1 through hn, whether man I gets their hat back, that happens with probability 1 over n. And so if you add up all the expectations here, of course, if a man gets their hat back or doesn't get their hat back, that's actually going to influence whether the other people get their hat back. So they're not independent, but we don't need independence to get expectations. So h being the total number of men that get their hats back implies that the expected value of h is the expected value of the sum, which is n 1 over n's. So on average, one man gets their hat back, and using Markov, the probability that the number is greater than or equal to n, it can't be greater than n, right? It can't have more than n men getting their hats back. But anyway, it's bounded above by the expectation divided by n, okay, which is 1 over n. Which sounds okay, but really the number of ways to scramble up the hats is 1 over n factorial, which is actually far away from 1 over n, right? Okay, so this is not a very tight bound. Go to this second example where it's around this lazy Susan. There are actually only n configurations, but the indicators work exactly the same way otherwise. Okay, so let hi indicate a match. Okay, and the particulars are exactly the same as before. Okay, so the expected value of h is still 1, okay, and you can verify that sort of mentally. Everywhere it's 0 except for one case where it's n. Okay, and so anyway, over all those n things, we divide by n. That gives us 1. And using Markov again, the probability is the same. Okay, it's the same as the previous one, except the probability is 1 over n that you get all n back. Okay, so this is tight, and this is the tightest that you can get, right? And this is sort of the worst case. This is how we base Markov's theorem initially, right? Sort of looked at the way of packing everybody in, and the best we could possibly do is shift everybody except for the cases we care about to 0, and then have the ones minimally at n. Okay, and that's exactly what's happening here. Everybody is at a 0 except for that. So this is really not tight, and most of the examples that we saw were not tight, but it is possible to get tightness. Okay, and so Markov is sort of all over the map, yeah? Yeah, exactly. That's exactly right. I'll just repeat it for the rest of the room. So, yeah, can we say because of the circular table, if one person gets their appetizer back that they all do? Yeah, that's exactly what's happening. So the score is either 0 in most cases, n minus 1 cases, or it's n in the case of 1/10 at the time. Okay, to the refinements. Okay, one refinement is to have a new minimum. Okay, so if we have extra information such as here, we say the IQ can't be less than 90. Okay, so in the initial case, we said IQ can't be less than 0, okay, which is true, but because SFU is such a smart bunch, most university bunches are smart bunches, the IEQ is not going to be less than 90. Okay, SFU students are also going to have above average IQ overall for the lot, so it's going to be 105. So we have extra information, and we ask ourselves the question, what's the probability an SFU student has IQ greater than 150? Okay, in the previous case, that was 2/3. Okay, so not a lot gained from the bound there, right? And there aren't a lot of people that have IQ 150 or more. Okay, probably very few of you here at this university have that kind of level. Okay, but if you have this extra information, you can do something cute. And the cute thing is, just by sort of envisioning the graph, right? Originally, we knew that it was greater than or equal to 0, okay, with an average of 100. Here, we're sort of making this artificial line at 90. Okay, and because the counterweight can only go so low as 90, you can actually get a better bound. Okay, and here's how you do it: you define another quantity that is non-negative. Okay, and you riff off of that. Okay, so let t be IQ minus 90. If you do that, IQ is definitely going to be greater than or equal to 90, so t is going to be non-negative, and we're going to use Markov's theorem on that. Now, in order for us to use Markov's theorem on this, we're going to have to find the expectation of t, of course. Okay, so the expectation of t is the expectation of this above here, which by linearity is the expectation of IQ minus 90. IQ for SFU is 105, so that will give us 15. Okay, so this value is the value we're going to sub in for Markov. Now the one that we want, right, we want IQ to be greater than or equal to 150. So t is going to have a different bound for that too. What are we going to bound for t if we know IQ is at least 150? What are we going to look for t? $60, yeah. 150 minus 90 is 60. I'll pretend I didn't hear the other number, yeah. Okay, so 60. And if you don't know what to do, you can just do a little bit of equation math inside the probability brackets. And this is going to be common for us going forward. Okay, so the probability of IQ greater than 150, we can sub in for IQ. This is the probability that, I guess, t plus 90 is greater than or equal to 150. And then pull the 90 onto the other side. Okay, so if you're ever lost, you can always write down what you want, sub in the value that you have as the other equation, and then solve. Okay. So this bit here is the thing we use for Markov. And that's less than or equal to the expectation divided by the 60. Okay, and the expectation here is 15, which is 1/4. Okay, still not a great estimate because 25% of you are not hyper intelligent, but it's better than the 2/3 that we had before. Okay, so the extra information is clearly helping us. Okay, just a couple of notes, and there will be an assignment problem that you can try on your 6th assignment. If you have a lower bound that's different than 0, you can rescale like the way we did it here by subtracting off b as the new lower bound. Likewise, if there's an upper bound, you can invert this thing and do like u minus r, which will also be non-negative, apply Markov. So as long as you have a bound on one side or the other, you can do something, okay, just by transforming the problem. Okay, so keep this trick in mind. There's only so much we can do by knowing the expectation, but Markov did his best. Okay, what if you know the expectation and the variance at the same time? Okay, this is Chebyshev. Okay, so Chebyshev allows you to refine your estimate usually, okay, better than Markov. And here's how it goes. Okay, so if you know the expectation and you know the variance, then this is the distance. Okay, so the way we read this. Okay, so this is how far does the random variable get from its mean? Okay, so the distance r from the mean. Okay, so distance from the mean. Okay, so how far does r get away from its mean? Okay, so if it's far away, if it's x far away, then the probability is bounded above by the variance of the variable divided by x squared. Okay, I'm just going to put a box around that for now so that I don't encroach on it later. Proof. We're going to use Markov's inequality actually to prove this, but we're going to fold in the extra information as follows. Okay, first of all, this thing here is very, very close to some other equation that we're used to. Okay, and that is, not just the absolute value, but the squares. Okay, so the sums or the expectations of the squares. Okay, so if we wanted this quantity, the probability that r strays from its mean, so the probability that it's at least x away from its mean, we can actually square both sides of this, and it would be the same probability because this, r minus the expected value of r all squared is greater than or equal to x squared. That's the same equation. Okay, same equal probability. And this bit here is just another random variable. And I could write it down. I could say let t be or x be this, and then rewrite it as x greater than or equal to x squared or t greater than or equal to x squared. And then we would do the expectation of t and then sub it back in. We don't need to do that. Okay, we're just going to treat this as a random variable. And using Markov's inequality on this random variable, okay, if this is bigger than or equal to x squared, Markov says that your probability is going to be bounded above by the expectation of this divided by the right-hand side, x squared. Okay, so by Markov's theorem, we get that. And of course, the expectation of r minus its mean, that's the definition of variance. Okay, so it just drops out, lickety-split. Now there's another version of Markov's theorem that is going to be handy for you, so I'm going to write this thing down as well on the slide. Okay, so two versions of this theorem. Okay, so the distance from the mean here, same thing. Okay, so the distance from the mean, so r minus expectation of r, is at least c sigma r. Okay, so remember sigma r is the standard deviation. Okay, so so this means how many, this is like c standard deviations from the mean. Okay, so the probability that R is at least C standard deviations away from the mean is bounded above by 1 over C squared, which is very nice and clean. I'll put another box around that. And it's more of a corollary than anything. There's nothing really exciting here. Instead of having X, we can sub in C sigma R. Okay, so let's just quickly do that. So this would look like the probability of R minus the expectation of R is greater than or equal to C sigma R. Okay, according to this theorem, it's going to be less than or equal to the variance of R divided by C sigma R all squared. And of course, the variance and the sigmas, right, they're related by the square root, right? So, we can let's just sub in for variance of R. So this would be sigma squared. Okay, so almost trivially, these things divide away. 1 over C squared. Okay, so we have a couple of easy examples to go through, and then one big one to finish off today, all right? But we're going to apply one or both of these things as we go through. Okay, but a very handy theorem. Okay, if you know the variance, you don't even have to know the distribution. If these are the things that are given to you, the expectation and the variance, you can do a tail inequality. Okay, just from that, which is kind of cool. Yeah, it's C times So the standard deviation is sigma R. So you're talking about C standard deviations from the mean. That's what C sigma R represents. Okay, so let's give it a try. Yeah. Okay, so suppose you know the standard deviation is 15. Okay, that is actually the way IQ is calibrated. It's normalized to be expectation of 100 with a standard deviation of 15. So what's the probability of an IQ of 300 or more? I mean, it's 0, but whatever. But we're going to bound it. Okay, we're going to bound it using Chebyshev and 150 or more. Okay, so same sort of question. Remember what we got in the previous example from Markov was 1/4 with all the extra information. Okay, let's try it with Chebyshev. Okay, so the expectation of IQ is back to 100. The standard deviation of IQ is 15, which means that the variance of IQ is 15 squared, which is 225. Okay, and we're asking ourselves, what's the probability that IQ, the difference between IQ and the mean, which is 100, is greater than or equal to X? Okay, so this is going to be less than or equal to bounded above by the variance of IQ divided by X squared. Okay, but if we sub those numbers in, so let's just quickly do that, the probability that IQ, minus 100, that's one of the quantities we know, is greater than or equal to X, is less than or equal to 225 over X squared. Okay, in order for us to use this thing, we just have to pick what X is. Okay, so we have 2 cases to deal with. Okay, we just need to pick X in 2 cases. Okay, let's do the first case. IQ is greater than or equal to 300. What's X in this case? It's 200. Yeah. Okay, so that we want the difference between IQ and 100 to be, at least something, but it's got to be, 300 away, right? So X is going to be 200. Okay, so the probability that IQ from 100 is 200 away from it, that would get us 300, okay, is bounded above by 225 divided by 200 all squared. And you ran that through a calculator, and you end up getting something that's less than 1%, which is good, right? The previous, when we did vanilla Markov the first time, we said this is less than or equal to a third. Well, okay, this is a way better estimate, way better. For IQ greater than or equal to 150, the distance from 100 is 50. Good. Okay, so that's less than or equal to 225 over 50 squared. And that's actually equal to 9% on the dot. Okay, so a little less than 1/11th. Anyway, good improvements, right? Okay, good improvements. Okay, so you have this extra information. Okay, let's revisit another problem. Okay, bounding a binomial. Okay, I asked this problem earlier. I said it's pretty easy to see that the probability of you toss n coins, n fair coins. What's the probability that the tail, okay, so beyond, is above 75% of them are heads, right? 3/4 and It's pretty easy to see it's going to be less than a half. Markov told us it was less than 2/3. Well, big whoop. Okay, Markov wasn't very useful. Let's try Chebyshev, yeah? Okay, for us to do this, we need the expectation and variance of Z. And you're in the middle of doing your assignment, I know, but this is always good review and keep you on your toes. So let's do it. What's the expectation of Z? Okay, and what's NP? Simplify it a little bit. N over 2. Yeah, P is a half. So this is N over 2. And what's the variance? Sorry? Yeah, so it's NP times 1 minus P, so that's a half and a half, so that'd be N over 4. Okay, so, right, so it's P, 1 minus P, which is N over 4. Okay, so we're looking for how far does it get away from its mean, and the distance from the mean here is going to be at least N over 4, right? Because we're looking for all the cases where it's greater than or equal to 3/4 N. Okay, so that's going to be a quarter N away from the mean. Okay, you can do this by doing equations, or you can just intuit it in this case, because it's just fraction math. Okay, so the probability that the distance from the mean is at least N by 4 is bounded above by the variance of Z divided by N over 4 all squared. So we have N over 4 divided by N over 4 all squared. I can do that in my head. That's 1 over N over 4. Now, there's a nice trick you can do, especially for this particular binomial. This particular binomial has an interesting property in that it's symmetric. Okay, it is 100% symmetric in its distribution. So this thing here is actually taking both tails, right? Because it's the distance on either side. You can go plus or you can go minus. So, it's actually taking the bottom quarter as well as the top quarter in its tail estimate, right? Here, it's also, the tail is kind of hard to see because it drops off really fast, but it's taking both of these tails in its computation. Right? Okay, so both of them are being taken, but we only care about the upper bit. Okay, but because it's symmetric, the upper bit must equal the lower bit. So if we're bounding this thing by 4 over N, really we can do better by a factor of 2. Okay, by using symmetry. And any time that you can find symmetry in a case, you should do it. Okay, so you should just take advantage and divide by 2 usually. Okay, but Z is symmetric, so divide by 2. Okay, so the probability of Z minus N over 2 is greater than or equal to N by 4. And notice I haven't written the absolute value brackets in there. We're just taking the one-sided tail this time. Is bounded above by a half of this estimate that's given above, which is 2 over N. Okay, so just to give you some context about what's going on here, let's try some values. I mean, this value here drops off, kind of rapidly as N goes up. This thing drops off by, it's like a polynomial at least, right? Okay, and if we try N equals 10, which is this case here, the probability that Z is greater than or equal to 3/4 N is less than or equal to 2 over N. That's a fifth, which is not bad. Okay, so if you actually do the computation, it's around 5%. Okay, so 20% versus 5% is way better than Markov, and it's, it's within some, it's not off by an order of magnitude anyway. It's okay, right? It's okay. N equals 32, which I've drawn here. The probability is going to be bound by 2 over 32, which is 1/16. And if you look at the picture, right, the values aren't even sort of registering in scale, right? So you expect that the sum in here is going to be small. It's actually very small. It's less than 1%. Okay, and 1/16 is about 6%. This is 0.35%. It's off by an order of magnitude. Not great. And N equals 100. The probability is less than or equal to 1/50th. And even then, it's non-zero, but it's pretty damn close to 0. This is 2%. The actual is 5.6 times 10 to the minus 7. Okay, so that's on the millionth scale. Okay, so it's 1/millionth of a probability. Okay, so very, very close to 0. So that tail bound of 2% is actually way, way, way too big. Okay, so it doesn't scale up very well, but it is a better approximation than Markov. Okay, questions about this before we go on? No? Okay, one more thing, and it's almost a trivial thing. These are known as tail inequalities, by the way, because we're asking how probabilistic is it that we're far away from the mean. Okay, so we're computing the sum of this tail, and we're bounding it. The inverse question, or the complement question, asks how likely is it that you're close to the mean, okay, within some bounds. And so this is known as a concentration inequality. The other is the tail inequality. Okay, so you ask yourself the question, how far is x away from its mean? Okay, so if it's within x of its mean, okay, so that's the inverted question. And you can just use the rule of complement on this to get what we had before, which is x minus mu is greater than or equal to x. And then apply Chebyshev to this. Okay, so it's a negative value. Okay, so it's bounded above by something negative. So this is going to be greater than or equal to bounded below, because it's negative, by the variance of x divided by x squared. Or if it's c standard deviations away, then it'll be 1 minus 1 over c squared. Okay, so this one is the inverted question. Okay, from this. Okay, so that's your second approximation, and there's a third one, which I'm going to introduce to you on Friday. Okay, it's called a Chernoff bound, and it's going to, most of the time, give you something that converges faster than Chebyshev. Not always, okay, but it's going to give you an alternate thing to use. Okay, so let's take a little bit of a breather. Okay, so the story so far, if you just know the expectation, you can use Markov's inequality, and there are two versions. One is that you just ask, straight up, is it greater than or equal to x? IQ is greater than or equal to 300, and you just divide by the x. You divide the mean, 100 by 300, you get a third. Okay? You can do c times the number of means, and you get 1 over c. That's kind of clean. Chebyshev, if you know both the expectation and the variance, you don't need to know the distribution. Actually, if you know the distribution, you can do some much finer computations. But if you don't know the distribution, but you do know the variance, or you know the standard deviation, you have two versions of this. Okay, so one divides the variance by x squared, and this is a distance function. Or you can look at distance from the in terms of standard deviations, which gives you, again, this nice clean 1 over c squared, right? So it grows like a quadratic, this grows linearly in the denominator. Okay, the inverse questions are over here. Okay, so the inverse versions are over here, the concentration versions versus the tail inequality versions. Okay, questions before we do the voter poll? Okay, elections seem to be happening all around us, and we do have two front-runner candidates. Well, I mean, you don't really vote for the prime minister like you vote for the president, okay, in another country. You vote for your candidate in your riding or your party, but, let's just say that it's preferential. Let's just say that these two are the preferred front-runner candidates. And, as of a couple days ago, they are pretty close. Mark Carney's got a slight edge, about 41%, I believe, versus Pierre Poilievre, who's just hovering below 40. Okay, so it is a tight race. And just imagine you're a pollster, okay, and you want to run a poll. And in doing this poll, your goal is to try and estimate, the probability that someone, any random person, would vote for either of these two candidates. Okay, so in a world where, these two candidates are the question, would you vote for this person or this person? What do? Well, you call up n people. Okay, so you call up n people, and you do it in this maybe perhaps strange way. You select n people uniformly and at random, and you're allowed to ask them more than once. Okay, so you roll say there are 20 million eligible voters in Canada. You roll a 20 million sided die. You pick a candidate. You give them a call, and you ask them a question. Maybe some people call you, right? Because you can vote. Some of you, probably most of you, and they ask you the question like, who are you going to vote for? And then you tell them. And it's possible that 20 million sided die comes up the same number again. Okay, and there's a reason why we do this. Okay, but we ask n people, and then we use the results of that to estimate p. Now the goal here is to estimate p using, and these are things that you've heard of if you haven't done these computations before, you've heard of them like on TV, okay, when they tell you statistics about stuff, okay, and the two things are reasonably accurately and with high probability. Okay, I'll talk about those in just a second. First of all, why do we select n people in a way that we could pick the same person twice? It's because it's independent to do it that way. Okay, so our choice of selecting whoever is independent, if we are allowed to select the same person twice, it may seem more efficient to select a subset and maybe more representative, but then it's not independent anymore, and a lot of the math that we would like to use breaks down, and we don't get any real benefit from it. Okay, so that's why we do that. Reasonably accurately and with high probability, you have heard the phrasing, right? This number is accurate to within 2%. right? This number is accurate, plus or minus 2%. So they put sort of error bars around it, where they believe, P likely is. P is a true number. We're estimating P. With high probability is our confidence level, and you normally hear things like 9 times out of 10, right? Or 19 times out of 20 is another common one, or 99 times out of 100. 19 times out of 20 is probably the one I hear the most, right? When you hear the studies, right, on TV or the news, right? Yeah, you've heard this before, right? We are confident 19 times out of 20 we suspect Mark Carney is going to win the election. So something like that. Okay, so this here is known as our confidence level, and it generates something called for the reasonably accurate, it's a confidence interval. Anyway, confidence level, 90%, 95%, or 99% are the typical levels. So say 9 times out of 10, 19 times out of 20 would be this one, and 99 times out of 100 would be that one. Okay, so the values here that we use, P is within plus or minus epsilon. Okay, and delta would be the error rate that we're actually outside. Okay, so that we're in the tail, we're far away from the mean, will happen hopefully rarely. Okay, but delta in the 90% case would be 5%, I guess. This would be 2.5%. That would be 0.5%. Okay, so let's give this a whirl. Okay, so the people you poll are chosen randomly, and their responses are mutually independent. This is maybe a lofty assumption, because maybe the responses are not independent. Okay, because I don't know about you, sometimes I talk politics with people, and they talk politics with me, and we might influence each other. Okay, so this might not be the best assumption, but in order for us to proceed, we have to make it. And we let xi be the indicator that the ith person prefers Carney over Poilievre. Okay, and then we total them all up. Okay, so S sub n is the sum of all the people that prefer Carney, and we estimate P by adding them all up and dividing by n. Okay, which seems maybe weird, maybe it seems normal. Okay, we're dividing by n. Okay, on average, n is the average, or n is the total. Okay, we have some questions here, and you're going to answer them. What's the distribution of x sub I? Bernoulli, yeah, Bernoulli what? P. Okay, the probability that they prefer Carney is P, so it's a Bernoulli. They're either like him or they don't. What's the distribution of Sn, which is the sum of all the xi's? Binomial. And what's the parameters in the binomial? Okay. NP. You ask n times probability P, that they're saying yes. And the expectation of this value, okay, so this value here, I hope it converges to P, okay? Otherwise, it's not going to be a very good estimate. Okay, let's see if the math works out. So the expectation, Sn over n, if we use linearity on the 1 over n, we can just pull that out. And the expectation of Sn is NP, right? Yeah, good. Okay, so all we have to do is poll enough people that we're confident enough that that P that we're estimating, this value Sn over n, is a good estimate of this P. Okay, it's not too far away, and we're confident enough. Okay, so we're going to parameterize this by the epsilon and the delta. Okay, so epsilon here is going to be 2%. Okay, so we're going to hope that this probability, whatever it is, right, the pollsters say it's around, a little over 40%. So they say plus or minus 2%. Okay, so the difference between Sn over n and P is less than 2%. Okay, so the chances is a concentration inequality. The chances are that this is going to be greater than or equal to 1 minus delta, where delta is 1%. Okay, so it's going to have 99% confidence that that number is 2% accurate. Okay, so just once again, okay, so this is our confidence interval, and this is our confidence level. And just to unpack this math here just a little bit, okay, because I know these absolute value things are a little bit, you don't do this a lot, okay, but you're allowed to be off between P and the estimate that we have by plus or minus epsilon. Okay, so this would mean that it's Sn over n minus P is greater than minus epsilon, bounded above by plus epsilon. If you were to maybe put the P out here on either side, you get P minus epsilon, p plus epsilon. Okay, or another way of saying this is our estimate is going to be within the range p minus epsilon or p plus epsilon. Okay, so our p is a defined, like it's a constant, right? The true p, we have no control over that. We're just estimating that p, right? Okay, so our value we hope falls within this range. Okay, we're going to use Chebyshev on this, and when I introduce Chernoff for you on Friday, we're going to redo this problem using Chernoff. Okay, and Chebyshev seems to look a lot like this. Okay, so using Chebyshev, the probability that this quantity from the true value p is less than epsilon is greater than or equal to 1 minus the variance of this quantity, Sn over n, the one that we measured, divided by epsilon all squared. Okay, and the form we want here is 1 minus delta. So we need this right-hand side to be less than or equal to the delta we want. So we need to find n, and it's going to be a big number, such that the variance of Sn by n over epsilon squared is less than or equal to delta. Okay. One issue is this. Okay, so let's figure out what that is. So what's the variance of Sn by n? The variance of Sn by n, we divide this thing by n, so that scales by the square. Okay, and that's just a property of variance. And the variance of a binomial is, in the interest of time, I won't quiz you. Okay, this is n times p times 1 minus p. And one of those n's cancels out. So we end up with p times 1 minus p over n. Now, I don't know if this is a chicken and egg problem, because I don't know what p is. And we should go into this not knowing what p is, right? Because we're trying to predict what p is. I don't know what p is. P could be anything from 0 to 100. It's probably somewhere in the middle. But all we need is a bound, okay? Down here is a graph of p times 1 minus p between 0 and 1. And you see it's a parabola, right? And it's a parabola that's centered at a half. And it's facing downwards, right? Because it's got minus p squared in it. And the maximum of that is a quarter. Okay, so max of p times 1 minus p is a quarter. Okay. Okay, so we're going to approximate this p times 1 minus p by a quarter. Okay, I have enough time to do one more step, and then I'm going to call it here and finish the final step on just a video, okay? Because I don't want to carve up the next class by doing this last step. Okay, so we'll sub this thing in to this equation. Okay, so the variance of Sn over n by epsilon squared is less than or equal to delta. This value here is less than or equal to 1 over 4n, so